Okay, so your assignment number 2 has been released. Oh, sorry, forgot to switch. There we go. Your assignment number 2 has been released. It's basically just on singly linked list. Not too much to say. I think the instruction itself is pretty clear. I cannot emphasize more. I just want to talk about 2 things. Okay, so in singly linked list that you're going to work on for assignment number 2, it is something called generic singly linked list. That one is going to require background study about generics in Java. So I don't really assume that necessarily for this course, but since you guys learn about polymorphism, dynamic binding, casting, that's something I definitely assume. Once you have learned those stuff, it's really easy, not difficult. It's really easy to catch up with the generics. So I got all the references on the assignment instruction there already. I'm going to also show you 3 slides that you already got. Guys, you have to make sure you catch up with that generics. It's going to be necessary. Starting from next Tuesday, maybe the second half, and also Thursday for sure, we're going to also assume you're going to know about how to write, kind of work with the generics. But you also got time to also catch up the basics and then reach out to me if you got any trouble understanding it. Again, I cannot emphasize more. Generics, we are not going to talk about it from scratch in class. Unfortunately, we're going to focus on other stuff. You really have to catch up with that. It wouldn't take you more than, let's say, 3 hours, right? Really plan your time before next Tuesday. And if you look at the slides for linked list and array, I'll show you where you should really go to, right? If you go to the arrays and linked list, which we're currently talking about, if you go to slide 33, I believe, right? Let me just go there first of all. All right, slide 33 basically kind of give you all the references that you will need for generics, right? Slide number 33, 34, 35, and 36. So these are the 4 slides I will need to assume you guys know how to really manipulate the generics at the basic level. You'll also get a chance to practice that a lot for assignment number 2, right? Required, right? No way around, sorry. You gotta learn that. But my office hour, way open. If you want to discuss anything about confusion, about generics, just come, right? But you gotta reach out, right? This will be the only time I'm gonna mention about these requirements that require study, all right? Please do that. All right, so there's also some recommended like extra problems on singly linked list. You might want to try them out, optional, if you feel very comfortable, just from the basic example that we discussed in the class, you don't need to look at them, optional. But if you want to look at some extra problems before tackling the assignment questions, you can also refer to them, right? So they are all in the instruction, pretty clearly laid out. All right, assignment number 1, solution, go over them, let me know. And split array harder, I will give you the solution and some video tutorial, thanks to your fellow students. And I'm going to do that over the weekend, right? You can expect to hear back from me, right? So you can also study that. Notes template, as usual, just on the page. I just did some updates late evening yesterday, so you can also re-download it if necessary. Also, office hour, TA hours, all the same. All right? All right, any question? If no, I would like to actually, it's your fellow student who raised that question here today. Maybe he got stuck on traffic today, I guess. All right? I want to revisit this one here as a recap, right? That one is definitely a very good point raised by your fellow students. I also already clarified that in the evening on Tuesday. So let's also clarify that right now. It is important. So whatever we said last time was completely okay, nothing wrong. But there's one thing I need to add as well. But just recall what the problem is. We talk about we having insertion sort, we got selection sort, and we know about the cost being increasing for insertion sort, and symmetrically for selection sort, right? That's kind of the background we know. And we had this kind of idea to have a hybrid algorithm to somehow say we want to perform insertions for the very first half to build a sorted area of size n divided by 2. And for the rest of the n divided by 2 unsorted area, we're going to do that by selections, right? That's all we said. And you guys were pretty good for part A. You guys all guessed right about the algorithm. The hybrid algorithm is going to perform just the same as before, n squared. And part B, we justify it. It's going to be n squared, right? All good. However, this is the part I'm going to clarify right now. Is this hybrid algorithm about sorting always going to work despite the contents of the input array? So some of you are already spotted that. That's pretty good, better than I am. So I think now I want to clarify that point. And then I want to do a little bit of practical logic to really make that condition formulated, precise. I think that's also very nice. All right, let's consider one example. Okay. Let's say I'm going to put it here. I'm going to give you one example that is not going to work for this hybrid algorithm. Okay, I'm going to put not working. Let's consider the input array that goes like this. Let's say 2, 1, 7, 3, 4, 0. All right, I claim that this array over here, if you try to do selection sort alone, it's going to work. If you do insertion sort alone, it's going to work. However, if you do the hybrid one, it's not going to work. Let's see exactly, right? So according to our strategy here, we are going to conceptually think about we're going to do the insertions up to this point, halfway, right? And then let's see what's going to happen. If you try to do insertions, that means we're going to process these 3 elements, right? So I assume that you guys already know how the insertion sort works. So what's going to happen is this half over here will be sorted after the insertions, right? It's going to be 1, 2, 7. And this half over here remains unsorted. 3, 4, 0. All right, so to be a little bit more precise, let me just make it thicker. All right, so this part here completely unsorted, and now we got half sorted by doing insertions, right? So let me just make an annotation here. So just by doing insertions for the first 3 elements, half. And then for the second half, let's now do selection, meaning that we're going to select the minimum from the unsorted area. The first minimum, what are we going to select? 0. And then followed by 3, followed by 4. 0, 3, 4 themselves are sorted. But the problem is, if you try to append that sorted sequence to the end of this already sorted sequence that's already half, you're not going to get a sorted sequence. That's the problem for the hybrid algorithm. All right? So I'm going to say we're going to do the equal number of selections. After that, we're going to get 1, 2, 7, which is already there. We don't touch it, right? We're just going to keep selecting minima and appending to the end. So we're going to get 3, 0, 3, and 4. All right. Apparently, you can see that this is not a sorted array. No way. Funny enough, this part here is sorted, and this part here is sorted. But if you combine them, they are not sorted. Useless. All right. So this one tells you the algorithm doesn't always work unless you add something called a precondition. You may have heard about the term before. Very simple idea. So in order for this hybrid algorithm to work, there's certain assumption we have to make about the input array. If that can satisfy that assumption, then it's going to work. All right, let me give you just one example where it's going to work. So I'm just going to put a cross over here to say it doesn't work, right? What about some example where it is going to work? So I'm just going to put over here to say something that's going to work. I'll just say working here. All right. The example will be, let's say 201. And then 473. Right? So this is going to work. And I can let you guys kind of convince yourself in detail, but very quickly. When we do the first 3 insertions, we're going to get 0, 1, 2. And then what would be the next minimum to select? 3. And then 4. And then 7. Right? So that one's going to work. So this hybrid algorithm here is not completely useless. You just got to specify the appropriate precondition. All right. So you guys can think about this particular precondition, but I'm going to tell you the answer right away. If the input array you're given, somehow the left half got all its elements less than or equal to each element in the right half. If somehow they can satisfy this condition, then this hybrid algorithm is going to work. All right? You can think about that inside. It takes some time, right? For those of you who haven't got it yet. But now the challenge is, whenever you want to specify precondition, you want to make it as formal as possible, so there's no ambiguity about what's being required for the input. So what I'm going to do is, I'm just going to put right over here about the precondition. And before I start with the precondition, for which we're going to use a universal quantification. All right? The idea is kind of simple. Think about you're given an array in general, let's say of size n. We know that how the hybrid algorithm is going to work is it's going to somehow do n divided by 2, the first half, and n divided by 2, the second half. The idea would be you want to choose some arbitrary element from the left half over here of index I, and choose another arbitrary element from the right half. Let's call it index j. I and j, of course, can be any combination, as long as I is in the left half and j is in the right half. Then we want to make sure the input over here at index I, let's say this is the input array, should be less than or equal to input at j. But now the tricky thing is, what should be the combination for I and j? We can do that very easily mathematically. All right, let's now do that. And we keep our assumption that n is an even number. So when we do n divided by 2, you gotta get a whole number rather than a fractional. So I'm gonna put it here. For every, all right, and we're gonna have 2 dummy variables, I and j. And what should be the range for I? It should be from basically 0 all the way to n divided by 2 minus 1, right? That's the indices, starting from 0. So I should be 0 less than or equal to I, strictly less than n divided by 2, right? Only up to n divided by 2 minus 1. And also j should be starting from n divided by 2, strictly less than n. So the last one will be n minus 1. And then we can easily just plug in this equation here that we talk about, right? Let me finish this and I'll recap once more about this example here, which turned out to be very nice. All right, so that will be the formal precondition using what you guys were supposed to know from 1019, right? Just predicate logic. All right. So think about this example here illustrates 3 things. Number 1, you have to get some intuition about whether some idea for the algorithm is going to work better asymptotically. That's part A. Just take a guess, right? Part B, you got to justify, like how I did it, to approximate or to count primitive operation, things like that, right? Part B. Part C is you have to think about, does the algorithm require certain input structure? Ideally, it should not. You should really just be able to sort any arbitrary array you're given. But for this particular hybrid algorithm here, it does require some input precondition. That's why we are discussing it, right? So maybe in the exam, I might just ask you exactly these 3 parts, one by one. But for the first part, that should be rather easy. But for part C, you can think a little bit more deeply about under what circumstances can the algorithm work. Okay. All right, guys, any question? All right, if you find this easy, good for you. If you find this very challenging, take some time to study that, right? This will be kind of the format you can expect in the exam, for sure. May not be about selection sort, insertion sort per se, but it could be about other sorting algorithm or maybe data structure. Yes?
Could you just go over what the precondition exactly is?
Sure. You mean the predicate logic here, right? Okay. So think about the diagram here. I'll make it a little bit bigger here. Let's say the input is any arbitrary array of certain size n. Let's assume n is an even number. Let's assume, okay? And we're saying that we divide the array into half. The first half has size n divided by 2. The second half has the size n divided by 2 as well, okay? And we're saying this. The input array is only going to make the algorithm work, be sorted correctly, if any element that comes from the left half must be less than or equal to any element that comes from the right half, any arbitrary. So for example, it could be 0, this, or it could be this one, or it can be this one, as long as one comes from the left, the other one comes from the right. And the way to really exhaust all the combination is by using, for example, for all over here. So we're saying I and j are the 2 dummy variables. I can be any number from this range, which is exactly the first half. And j can be this range, which is exactly the second half over here. So this range over here is going to make sure I and j are going to be considered for all the combinations as long as they're in the corresponding halves over here. And then we say that once we got an I and j, we're going to make sure this element here should be less than or equal to this element here. And you can also use this example to verify. And this is going to work. If you don't satisfy this input precondition, the algorithm is not going to work. For example, this one here doesn't satisfy it. Okay. Better? Yeah. Okay, great. All right, guys, I'm going to leave that to you, but do follow up with me if you still have trouble, right? No problem. I will consider this not trivial, okay? Okay, let me do the rest of the recap from last time. So last time we basically started with the singly linked list introduction. We talked about connected nodes using aliasing. Basically, got to watch out for the next reference, which we're going to see way more today, and also Tuesday as well. And then we talk about the possibility of null pointer exception. You got to really watch out for that. I would say most likely this will be the most common errors for your assignment number 2 and programming test 1 as well. Okay. And then we talk about here linear versus nonlinear, right? Make sure you understand the definition. And then we talk about absolute versus relative positioning. So in the case of the linked list, either singly linked or doubly linked, excuse me, you can also use the next reference to simulate the absolute indexing. That's something we'll see precisely why it is inefficient. Let's say, if I just want to go to certain position I in the singly linked list, in general, there's no way around. But you have to start with the head and go all the way to this position I by using as many next references as possible. So what's the worst case? When I is getting very, very close to the size of the list, n is going to be the worst case, which will be linear, right? So you can see that's kind of the thought process you want to have to really figure out the asymptotic upper bound. But I'll get to it more about code and tracing today. And we talk about 6 different cases and also some exercise for you. You can give a try. I would say these 6 cases are kind of account for most of the basic operation you're going to do for linked list. So make sure you kind of understand what's going on over here. I thought that might be the most intuitive introduction to the singly linked list. If drawing arrows and also drawing boxes really makes sense to you, it can really help you to translate the diagram directly into code. So what I normally do when I design singly linked list algorithm is something I try to draw the diagram first and see how I can translate each step in the diagram into Java code. It's actually easier, maybe for the beginner or even for advanced programmers. So think about it. And this was, OK, so and we talk about the Java classes, and we got 2 classes here. We got the node class, and as part of its definition, we got node over here again. It's called recursive type, which is very common. Once we get to the implementation for trees after the reading week, you will also see recursive type. Even more so, we'll see that. Okay. So for the node class, we assume we got elements, we got next, and we got another class called singly linked list. And most of the methods about algorithm of singly linked list is going to be defined in this particular class, singly linked list. We're going to see quite many of them today. And for now, we assume there's only one attribute of type node called head, right? We kind of visualized that last time. And once you create the singly linked list objects, you're going to set the head to the beginning of some chain of nodes. That's how you set it up, right? We're going to see example today. And we did a little bit last time, right here. So this is one way for you to build a chain of nodes without using the set next method here. I'll show you another version of the solution that's going to use the set next. You can choose whichever you like. This one here, I'm simply using the constructor over here for the node class. You can see as part of the constructor, we are trying to pass the next node, right, for that particular node. When you first create a node class, let's say if I say maybe Alan, and then if I simply say null, this is also possible. If I only set that, it's not going to set the next reference to any node. But what we're doing here is we are setting that to Tom and Mark, right? We talk about the detailed tracing for that. You can review it. And as a very quick follow-up exercise, I want to write some alternative version of the setup. And you guys can tell me if that's going to work. OK, I'm going to write it down from scratch. Because somehow your fellow student from the previous year, they kind of complain that it's very counterintuitive. I want to set up Alan, Mark, and Tom. Why do I have to create Tom, Mark, and Alan in the reverse order? You see, right? I can appreciate that. Why don't we follow what your fellow student was thinking? Okay, why don't we do the following? What I'm going to do is, okay, I'm going to move this a little bit upwards. I'm going to do something like alternative. You tell me if that's going to work. Let's say I got a node over here. I want to start with Alan, really. I would say Alan here will be a new node. And I know that, so this will be the name. And I know that Alan should really point to Mark. So why don't I point to Mark right now? And then I got a node over here. I got Mark. New node. This will be Mark. And I know that Mark should really point to Tom, right? Finally, I know that Tom doesn't point to anybody. So I would just say node over here, Tom. So this will be Tom. And I know that Tom should be the end of the chain, pointing to just none. How about this version here? Is it going to work? No? How come? What's going to happen at the runtime?
I'm not sure, but when you're calling Mark object is not created yet.
Aha, on the right track. So guys, when I ask you what's going to happen at the runtime, it's the wrong question. There's no runtime. It doesn't even compile. Okay, I hope you see that, right? Because it's a very fundamental thing, but it's good to brush up. We are now referring to Mark, who will be only created in the next line. Is that allowed in Java? Not any programming language, I'm afraid. Not even going to compile. All right? If you do that in Java, something like unknown variable. Compilation error. The reason I'm mentioning this is because if you do want to choose approach number 1, unfortunately, you have to start in the reverse order. There's no way around if you want to just use the constructor over here. That's the main point. Because if you follow exactly the order that makes sense to you, just not going to compile. All right? Hopefully that makes sense. Let's now move on to approach number 2, which you might prefer more, which is definitely OK. For approach number 2, which I'm going to show to you, that one there use just a little bit more lines of code, which is completely OK. Asymptotically, it's just the same, right? It's not going to run slower, really. All right. OK, let's say this one here. All right, approach number 2. We are basically going to create 3 nodes over here, Alan, Mark, and Tom in this particular order. In some way, that's good. We kind of follow the desired order that we want. And then the next reference for each one of them will just be none to begin with, let's say. All right, I'm going to draw that very, very quickly. Green, blue, pink. So this will be the first one. This will be the second one. And also this will be the third one. All right. So after this line here, we basically got Alan pointing to a node class. I'll just say n here. And then we know each node has elements and also next. Element will just be Alan. The node here will just be, the next will just be null. All right, very straightforward. And then the second one here is going to be very similar, but I'm going to draw it down. We also got Mark over here pointing to an object over here of type node. I got element, I got next. And this will be Mark, and then null. All right, the final one, just the same process. It's going to be Tom pointing to a node object here. And then I got element, I got next. So element here is going to be Tom. And that one there is going to be null, right? Of course, just by executing these 3 lines is not going to be enough because we haven't really set any relationship or connection between the nodes yet. That'll be the next 2 lines. The idea is very simple. What I want to do is, now that I got all the variables defined, I can say Alan.next should be Mark. Mark.next should be Tom. Exactly, right? So if you prefer this way of doing, no problem. All right? But you should understand how the previous one worked as well, even though that may not be how you write it in the assignments or programming test. All right, so when I say Alan.set next to be Mark, okay, for this one, I'll just trace just one more time, just in case you are still kind of struggling with basic tracing. So I'm going to, let's say when I execute this line, right, I'm going to call this method over here, set next, right? If you remember from 2030, every attribute access has the implicit this. Right? So now, since I'm calling the method with Alan as a context object, so this is going to be Alan. And then the argument over here, Mark, is going to be Mark. So N here is going to be Mark. So what I'm saying here is Alan.next will be Mark. Alan.next will be Mark. Right? That one is something you definitely should know. All right, if you go to the next line, you can do the similar tracing, but here I'm going to say Mark.next will be Tom. So Mark.next is going to be Tom right here. Right? If you compare this structure over here and this structure over here, completely the same. So two approaches will achieve the same thing. Asymptotically, they're also the same, just constant. All right. Any question here about this? So far, we only talked about how you can build a chain of connected nodes. We are still restricted ourselves to the node level. But let's see how we can bring the simply linked list class into the context. Pretty easy. The idea will be, if you already got some nicely connected chain of nodes over here, you just got to decide which one is the head. Well, obviously, this one should be the head. It's kind of the leftmost. So somehow we're going to create a simply linked list object and set the head accordingly. That's all we're going to do. All right. So again, let me show you on the slides. We just finished approach number 1, approach number 2 for creating the nodes. The next slide, approach number 1, approach number 2, is just showing you how you can build the chain differently so that it will impact how you set the head. Right? I'll show you quickly. That one's going to be quick. All right, so let's see this. So now we have switched the context to singly linked list right here. All right. And the one we're going to use will be the constructor, which will be, oh, by the way, there's no constructor here, meaning that we got a default constructor, right, implicitly. Which means you got something like here. So you can think about the singly linked list over here. That's a default constructor, which will just leave all the attributes of null value. Default constructor, right? But we kind of set the head to be null anyway. Okay, but you can feel free to actually put this initialize to be null in the constructor itself. It's kind of up to you, right? It's more programming details. And the one we're going to use will be set head, right here. Right? That's the method we're going to use, which will set just the head attributes to whatever node we are passing. Right? Easy to understand. I just want to show to you exactly how to visualize this. You can think about this part here, the first 3 lines correspond to approach number 1 about building the chain of nodes. I'm not going to repeat that part. We have seen that already, right? So that one there is basically from before. That one there is going to build exactly this chain of nodes. We can start from this. And then when you actually try to create, let's say, singly linked list, right? Let's see how we add an extra level. So it's going to be called list. So list is going to be the reference for a singly linked list objects right here. All right. And then you got singly linked list. Oh, at the moment, we assume that we only got head as the attribute. We're going to extend the attribute a little bit later, but for now, just assume only got head. So right after that line, it's going to be pointing to null. All right. And if you try one more line, let's say right here, if you say list.setHead to be Alan, that one there is going to set list.head equals Alan, which will be the arguments. Right? Alan is really pointing to this particular node. That one is going to say the head, rather than pointing to here, is now going to point to over here. That's it. That's how we link the chain of nodes into a singly linked list objects. Okay. And of course, you can see some aliasing over here. I'll just write it down here. Easy to see. If you simply say list.head, 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 it will be just the same as Alan, right? The same objects. Equals Alan. That should be true, right? Just one example of aliasing. Questions? All right, good. And the next one there, really the same thing, right? The only difference is the way you build a chain, just following approach number 2, like what I said earlier, right? So you can think about this part over here is the approach 2 that we spoke about, and that one there will just give you the same chain of nodes anyway, right? And then these 2 lines will just be the same. That one there, you just try to create a list and set the head, the same. So the list is going to point to, again, singly linked list objects, and then head. And that one there is going to point to wherever Alan is. That's it. The same way. It's just about how we build a connected chain of nodes. Right, there's one thing I also want to address very quickly about some special case. When we talk about singly linked list, right, always you got to consider edge case, like a special case. And because the list size can only start with 0, like a natural number. 0, 1, 2, 3, 4 cannot be negative. So let's now visualize very quickly. What's really an empty singly linked list? That one should be pretty easy. So basically, you got your singly linked list objects. Singly linked list. And for now, we only got head. And the head is simply pointing to none. Right? So you got some list. The reason I'm writing this down is because when you say, let me say the following. SLL, let's say list 1, equals new singly linked list versus SLL list number 2 is initialized to be null. Right? So this is list number 1, and this is list number 2. Somehow null appears somewhere, but you will only say list number 1 is empty. You wouldn't say list number 2 is empty. It's just null. It doesn't even exist. An empty list is still a list that exists. It's just that it has no head just yet. All right? That's something I want to clarify quickly. This one here is something called non-existing. Versus when I talk about list 1 here, it's just empty. Existing, but empty. All right, very important clarification. All right. All right, so after this, let's now move on. Yep. So far we talked about how you can build a chain of nodes and also see how you can set the head of the linked list. And let's now start talking about algorithm, basic ones, right? And do some tracing. Okay, let's go back. So the first one we're going to solve will be the problem is like here. Let's say you're given a singly linked list with maybe potentially either null head or maybe some non-null head with a chain of nodes. It can be either case, right? You got to consider. And we just want to return some integer indicating how many nodes are there, starting from the head. That's something we want to know, right? So for example, I'm going to show you the Java code in a moment. Let's say the list you're given is like this, right here. If you say list over here, it's a list.size. Size is a method that we're going to implement. That one there is going to say, starting from the head, how many nodes are there in the chain? In this case, 3. Right? That's something we're going to implement. We're going to implement the Java code, trace it, and also we're going to figure out the running time. All right. So hence, okay. So this will be a good hint. It's really about the specialty of the last node because we know that last node tells us we cannot really go any further for our counter increments, basically. All right. Let's now take a look at the Java code. Oh, by the way, so if you go to the lecture site, that's something I forgot to mention to you. You can see under the source code section here, I got singly linked list of string. So this source code contains all the example that we talk about in the class, including there will be some exercises I also leave as empty for you to try. But I'll try to give you some hints visually to help you a bit. I think that these are the basic ones. If you're already struggling with the basic one, get them done first before you tackle the assignments. Right? Assignment is definitely harder than the basic ones for sure. All right, let's now take a look at the first one. The first one here, let me switch to here. All right. So the example that we're going to use will be just this particular list, right? We got chain of nodes. The head is simply just Alan. Alan, Mark, and Tom, 3, right? And we got this method here just called getSize. It's an accessor that takes no parameter. And one thing also important to note, this method here is not defined in the context of the node class. It's defined in the context of the singly linked list class, all right? This is a singly linked list method. All right. And this method here, very simple, but I'm going to really talk about it for very thoroughly, just for there are some patterns you can definitely follow for even for the more advanced algorithm. One would be you want to somehow keep accumulating certain counter, or maybe string or array, right? Something you want to keep accumulating. And also the current is also something very useful. Because of aliasing, that we want to somehow keep track of where we are when we are trying to traverse the list from left to right. For array, you don't have to. You can just use a loop counter. But for linked list, you don't really have a loop counter per se, but you have to use this kind of thing. So what I will do is I'm just going to put some inside here you can think about. You can compare the current is like the loop counter when you're writing a for loop or while loop. It's a little bit similar to a loop counter. Similar. Not exactly, but similar purpose. For loop counter, you want to make sure I should be less than or equal to array.length minus 1. What about current? As soon as current somehow reaches null, you know that you're at the end of the list. That's where they are similar. All right. Let's now look at the line very quickly, and then we'll trace it. Okay. Each line. So we initialize the counter to be 0, and then we set the current to be just the head. You can see the head is pointing to Alan, right? So we're going to say this will be our current. So here's the idea. At this point, the size, I'll say S, is simply 0. When size is equal to 0, current is over here. And we're going to change the current and increment the size at the same time. Current is going to be moved to the next one. And then size is going to be incremented from 0 to 1. All right? And then current is going to be changed to the next one again. And size is going to be incremented to 2. And then we're going to increment this again. And this one will be actually going to null. And we know that now this will be the value to return. That's a very kind of vague sketch just to show you overall what's going to happen. Right? But I'm going to do detailed tracing to see exactly. You want to think about when you study this example here, you want to see how the size value and the current value somehow keep in sync with each other in some way. That's really the point I was trying to make, right? But let's see exactly how it's going to work. So let's now take care of the 2 lines right before the loop. I'm going to use a green here, right? So these 2, okay, right here. We're going to initialize the size to be 0, and the current is going to be pointing to just the head. The head is pointing to right here. Oh, sorry. The head is pointing to right here. And then the current is going to be here. Right? So that's exactly this line. That's how we start with. All right? So that's the current. And current is going to keep changing. It's a variable. And if you look at the while loop over here, I want to maybe remind you something very basic about while loop. Whenever you see a condition here that's a Boolean, it tells you as long as this condition is true, you're going to keep iterating, right? But sometimes it might be more important for you to also realize logically equivalent. When does the loop exit? Right? So if I look at current not equal to null, that tells me what's the logical negation of current not equal to null when it is equal to null. The loop is going to exit when the current equals null. So this is something very handy for you to also keep in your mind. the way you want to understand the loop is not just about under what circumstances it's going to keep iterating, but also under what circumstances it's going to exit. That's also important to get an insight. So as soon as we actually somehow update the current to be exactly equal to null, we're going to exit from the loop. So that guarantees termination for the algorithm. Okay? And then for every iteration, we're simply going to update the current and then also increment the size, right? That's exactly. For iteration number 1, right before that, at the moment after this line and this line here, I know that current is now Allen, right? Current is pointing to just Allen. And then I know that if I try to evaluate this condition here, I'm basically evaluating Allen not equal to null. Indeed, it's not a null object, so that's true. That means we're going to go for the first iteration. And then we're going to go for the first iteration. And for that first iteration, we're going to say current is going to be updated. Current is assigned to current.next. Current.next is the mark node. If I want to say current is assigned to it, simply update current to here. Right? Simple assignment to perform. All right? So when I say current is assigned to current.getNext, I'm basically going to say current will be mark afterwards. And I'm going to update the diagram as well. So current is now going to point to mark. Okay, let me say it again. For the very first iteration, we're going to do the first update. Current is going to be moved conceptually to the right by 1 node. So current is assigned to current.getNext. Current.getNext. So it's going to be updated to here. All right. At the same time, we want to increment the size. So size is going to be incremented from the initial value 0 to just 1. And then we're going to see if we have a second iteration. So when we get to checking if we have a second iteration, we're going to see the current right now is mark. And mark not equal to null is also true, right? You can see currently this is not null. So we're going to enter the second iteration. And for the second iteration, we are actually going to do the updates again. Right? Current equals current.getNext. So current, rather than pointing to here, is going to point to its next. So current will be updated to right here. All right? And then that one there is going to make sure current is set to Tom. Is set to Tom. And then at the same time, we also got to make sure we increment the size, right? For both iterations. When increment the size is going to be incremented from 1 to 2. Right here. All right. And then we're going to see if we need a third iteration. Before we check that, we're going to check the while condition the third time. So current right now is Tom. And we check to see whether Tom is not equal to null. Indeed, this node here is not null. Right? So we are just going to enter for the third iteration, and now here comes the important point, right? If you try that over here for the third iteration, current is assigned to current.getNext. So current is going to assign to current.next, which will be null. Agree? Right, so current right now will be null. And the size will also be incremented for another time, every time, right? So that'll be 3. And we have done 3 iterations so far. Is there going to be a 4th iteration? Seems like no. Because if you try to check the while condition for the 4th time, current right now is actually null. You're basically evaluating null is not equal to null. That one there, for sure, is false. And when this condition here becomes false, exit from the loop, no more. And when we return the size, we are returning 3, which is exactly 1, 2, 3. Right? That's a detailed tracing over here. But what's really important for you, number 1, you want to understand how to really initialize the current like a loop counter and keep updating it. Typically, you would just say current is assigned to current.next, but sometimes it may not be the case, right? You want to be alerted about what you should do. That's number one. Number two, there's always maybe some counter or maybe some value you want to keep accumulating as you go scan through the list from left to right. You also want to keep updating it as well, so that at the end you can return that value. You don't normally return the current, but maybe the value. But sometimes you do return the current. Depends. All right, let's now take a look at big O. What's the asymptotic upper bound, right? Once we have done the tracing over here, you basically you can now figure out exactly how many iterations there will be, right? You can see I got exactly 3 rows over here. That simply corresponds to how many nodes are there in the list, in the chain, all right? So you can look at right here. I can say the number of iterations is equal to the number of nodes in the chain, which will be just n. So the number of iterations is going to be big of n. And for each iteration, you can see we only do simple assignments, simple attribute access, so that will be big of 1. So it's going to be big of n in total. All right, so you also want to know how to figure out the number of iterations, and then for each iteration, you only got big of 1. So overall, big of n. It's a linear operation to figure out the size of the syncly linked list. You might be wondering, wouldn't that be a good idea if rather than calculating the getSize every time, we somehow store some attribute for the size? If you're thinking about it, that's good. That's something I'll talk about. It's a very, very common scenario where you have to think about whether you want to trade so-called trading space for time. I'll cover that a little bit later. But keep that in mind. But let's say if you're forced to really implement a method to get a size, no way around. It's going to be linear, right? That's the main point. I would just say over here, may be improved. To be continued. All right. All right, so that's our first simple algorithm on the syncly linked list. Let's see the next one. The next one is very similar, so I'm not going to do the detailed tracing. I'll leave the table clean, so you can also give it a try. So what we just finished is about the getSize. That one's done. All right, the tracing here, we also did it in complete details. Right, the one here is very similar. Let's just talk about it too. How do you find the tail of the syncly linked list? It's a very similar problem, basically. Rather than counting how many nodes are there, you just want to get to the last node without returning the actual counter, right? So, not surprisingly, if you look at that code over there, very quickly. The way you want to understand this, I'll help you a little bit with some annotation. So there are basically 2 variables we are dealing with. One is about the current, the other one is about the tail, all right, over here. So rather than having a size, we have a tail, all right, it's different, okay. So what we have, let me separate them. So let's say all the lines to do with the current. I'm going to put it here, current, and also current. Only these 3 lines have to do with current. Think about current here. It's just a loop counter, just for you to know how many iterations you will need to traverse the list, right? On the other hand, what we want to ultimately return is something called the tail. So this is one line here. This is another line here. So if you look at that, the green one is going to make sure the number of iterations for the while loop is going to correspond to number of nodes in the list. And then we want to make sure every time before we move the current to the right, we want to capture its value first. Eventually, we know that current is going to turn to null. So we want to make sure its previous value is caught by tail, so it will be returned. All right. So you guys can definitely try some tracing over here. I will highly recommend you try that. But let's now look at this diagram here, just see very quickly how things are going to work. All right. Let's say in the very beginning. So I have current is just pointing to the head. And then I have the tail just null. right? You can think about this part over here is exactly just right before the first iteration. Right before. That's a setup, initial setup, here and here. And I know that current is not equal to null, so I'm going to go for the iterations for as long as it's necessary. And then before I move the current to the right, I have to make sure the tail is actually capture its value before it's moved. Right? That's a key thing. So what I will do is I'm going to say, for the first iteration, tail, rather than pointing to over here, is now going to point to wherever current is pointing to. And then I'm going to move the current, rather than here, is going to move to the next node. That means current is always one node ahead of the tail. That's the interesting bit. All right? So this part here is the first iteration. So what I have just done was the first iteration. So think about this part over here is the first iteration. What about the second iteration? For the second iteration, I want to move the current to the third node. But before that, I have to make sure the tail will capture its value first. All right? So for the second iteration, I'm going to, again, tail will be just the current. So tail, rather than here, is going to point to the current right here. And then I can now safely move the current, rather than here, is going to be here. Still, you can see at the end of the second iteration, the current is still one node ahead of the tail. That's exactly the point. All right? So that will be the second iteration. So think about this part over here is the second iteration. This part here, right? Just right here. These are the two arrows we are changing. So that's the second iteration. But we need one more. The third iteration there is actually going to change before we modify the current, right now it's here. Before we change that to the null, right? Because the next for this node here will be null. Sorry, right here. Before we do that, the tail has to capture the current value, right? So what we'll do is now rather than pointing to over here, the tail is actually going to point to where current is pointing to, right here, right? And then we're going to update the current to its next. Its next is actually null. Right here. So this is the final iteration. Right here. So right here. Okay, so these two arrows tells you that's a final iteration, third iteration. And at the end of the third iteration, you can see the current is equal to null. That's exactly the exit condition for while loop, as we said earlier. So we're going to exit from the loop, and what's the tail? Well, Tom. Right? It's working. All right? Not too bad. I think this one here gives you also a little bit more insight about not just updating some integer counter, but we're updating two reference at the same time. And the one about tail is one position behind the current reference. That's what you want to watch out for. All right? All right, any question about this? Yeah.
Sorry, it's not about these methods, but like, would it still count as an SLL if we like say Tom.next equals Alan, or should we like define the exception?
Yeah, so yeah, over here, if somehow you got Tom.next is actually equal to Alan, in that way you got a circular list. It's not terminating. So that one would definitely cause you trouble. For example, if you try to run, let's say, getSize, then you will never actually satisfy current equal to null because you always just keep iterating. So you're just not going to terminate. So definitely for your syncly linked list, you got to make sure there's always an end that has the null reference for the next.
So we should like define exceptions.
Yeah, maybe define. You can either say, yeah, you can define some exception to make sure if, but typically you will be the implementer, right, for the method. You got to make sure you don't introduce any circularity to your chain of nodes. Yeah, for sure. Good. All right. Asymptotically, how would that work? Well, the number of iteration, as I illustrated, again, is 3, corresponding to how many nodes we have in the chain. Again, size of the list, n. All right, very quickly. So the number of iterations will just be the size. So the number of iterations will just be equal to the size of list. So big O of n. Right, you can see also each of the operation here for each iteration will just be constant, right? So overall, linear. There we go. All right, linear. Yeah, try to see if you can do some tracing along this line over here, right? That might be also very useful for you. Try Eclipse that'll be even better. Yeah.
I just had a quick question. For a doubly linked list, we would only need to store one value because once we see that the next is null, we can just go to the previous, right?
Yeah, we'll definitely get to doubly linked list in maybe not today, possibly not Tuesday either, maybe on Thursday. So let's say once we get there, we'll answer that question. Because your fellow students don't really have the concept about previous just yet. Okay, we'll get there. Yeah. All right, very good. All right, let's see. The tail is good. Let me say one more thing about trading space for time, and then we can take a very short break. Okay. If you go back to the slides, we're basically talking. So far, we talk about two methods, two algorithms. If you're forced to really figure out the size or the tail of the list algorithmically, meaning that you got to do some computation, it's going to be linear operation. But if you think about array, what will be the cost for getting the size of the array? A.length, for example, constant. What about getting the tail of the array? Oh, do you have A.tail? You don't. A at index A.length minus 1, right? Also constant operation. Can we somehow do something similar for the singly linked list? It turns out it is possible, but you have to understand that if you go for that particular design decision, there will be some catch you have to make sure you cover, right? That's something I'm going to talk about. Right? It is something called trading the space for time. All right? Let's see some little bit slides here. So that's about the tail, right, that we just covered. All right, tracing, you can take a look too. All right, can we do better? Specifically, can we somehow retrieve the size and tail of a singly linked list, not linear time? Can we do that constant time? That'll be the best. Okay, that's a question. But let's now see some motivation. It's very common to really say, given a list, I want to get to the end right away. Well, I may want to get the size right away. Maybe if there's a frequent operation you want to perform for your data structure, it better not be linear. It better be constant, right? Because it's going to be called so many times overall. Let's say if you want to get to the tail of the list, let's say you got a surface queue, right? Linked list is also a very like a surface queue, just in general, like a line. For Tim Horton, maybe for Starbucks, whatever. But you may want to go to the last customer in the queue, maybe move them somewhere to the front, something like that, right? You want to get to the end of the linear collection. So getting to the tail is a very useful operation to make it cheap. Similarly, you may just want to get an idea about how full it is for your surface cube. You want to know the size. So you don't really want it to be too expensive either, right? So that's kind of the motivation. So what we're going to get is something called trading the space for time. We're going to see this principle here, maybe at least for 1 or 2 times for this course. But it's a very nice general principle when you try to design your Java classes, right? Let's get into it, and I'll tell you exactly what you're going to watch out for, all right? So the idea would be we want to trading space for time. What does that mean? This one simply means waste more memory space to make subsequent computation more effective or cheaper, let's say. Computation cheaper. So when we talk about the space, when we talk about the space over here, it's really about memory space, right? And when we talk about the time over here, it's really about how much it costs to run the computation. We want to make the computation themselves cheaper. Okay, here's the idea. we are actually going to, well, you can see for now, we assume the singly linked list has only one attribute head. So whenever you want to get to the front of the list, it's very cheap. Just say list.head. We'll do something similar. We're going to extend our Java class such that we're actually going to have two more attributes over here. Okay, let me use different color here. We're going to have two more attributes here. One attribute here is called tail, just like the head. Another attribute is called size. Tail and also size. And of course, they should be updated periodically correctly. Otherwise, there will be some inconsistency. Right? So what do I mean? If I actually got the size over here, what should be the current value for size? It should be 3. Every time if I want to somehow change the list that's going to impact the size, I need to really increment or decrement it accordingly. That's something we'll see later. At the moment, it should be just 3. Right? What about the tail? The tail here is now going to point to just right here. So we're going to introduce these two attributes, which are basically data. They're going to occupy some memory space, but it's going to make our getSize and also getTail way cheaper, constant. You can just access the attributes, which is constant operation. All right, let's now do a quick summary about this approach over here. So now for the singly linked list class, we are going to have 3 attributes. We're going to have the head, and we're going to have the tail, and also we're going to have the size. And all these are the attributes. So that would imply more cost of space. So rather than having just head, we now also introduce tail and size. So we got more cost in terms of the space. But we think that's worth it because that can make the computation cheaper. So now, on the other end, when you talk about how we can, let's say we got SLL, let's say list equals new singly linked list, right? Let's say we got this object here, and then if we do list dot tail and also list dot size, so compare these two with, we say list dot getTail, list dot get number of nodes, like how we did it previously. These two attribute accesses are going to be very cheap, constant, right? So these two will be attribute access. So that means less cost for computation, less cost for runtime, running time. It's a trade-off, basically. Okay. So just very quickly, so this part over here should be just big O of 1. Just access the attribute. That's a good thing. But let's talk about the catch. The catch is, now whenever you're going to talk about different methods you want to implement for a singly linked list, you always have to be careful about, am I going to update not just the head, but should I also update the tail and size at the same time to make sure all the attributes are consistent with the layout of the list? That's very important. That's the catch. So we're basically saying we have better running time, but our methods implementation is going to be a little bit more sophisticated. You got to be more cautious about what you implement. All right, I'll write it down. So the catch will be for you as a programmer, which may not be too bad. So the catch. For methods that might impact head, tail, or size of a singly linked list. The implementation body, the bodies of the methods, right? the bodies of these methods must update them properly. All right, so that's a catch. Not for every method, but you gotta judge. Sometimes method may not touch the size, head, or tail. But sometimes you may have to watch out for. So for method that might impact the size, head, and tail, you have to make sure update them properly. All right, that's really the essence for the catch. All right. Of course, we're going to see example to convince you. All right. Any question about this so far? All right, that's pretty good. Okay, why don't we take a very short break for 2 minutes, taking attendance, and then we'll continue. All right, let's see where we are in the slides where we spoke about trading space for time. It's a very nice principle to bear in mind. We're going to see that again when we get from singly linked list to doubly linked list to apply this principle one more time. Okay, just keep that in mind. Right? It's a very nice principle to know about. All right. All right, let's now talk about another problem. That might be the last one for today. We'll see how long we can go. Let's say we want to insert. Let's say we get a singly linked list. We want to insert to the first. Right? Let's say this. This one is already the code, but I'll give you a very quick sketch. Let's say we already got Alan, Mark, and Tom, right? We got 3 nodes here already, and we're assuming that we got 1, 2, and 3 attributes. So this one tells us whenever you're implementing a new method, you got to watch out. Like these 3 attributes should be updated properly. There should be no inconsistency. Okay. When I say add first, if I say add first, they're basically saying the head is no longer this node. I'm actually going to say maybe the head is actually going to be over here, a new node, and this new node next is going to be the old head. Something like that. We did something very similar, right? Remember in the visual introduction, right? So when you see the code in Java, you shouldn't be too surprised about roughly how it's going to work. So what we're going to do is we're going to look at the Java code and trace it, okay? The solution has only these lines of code, not many, all right? But we're going to look at that. By the way, if you look at that right away, what's the asymptotic upper bound? Does it look like linear? Now, oh, did you say yes? No, okay. Yeah, there's no. It doesn't look like for, right? Yeah, it's not for loop. Yeah, exactly. So if statement only, right? So good, constant. That's a very good guess, okay? So that's now, but we're going to trace it. It's going to be interesting to see what's going on. When you guys actually download the source code I made available to you, on the lecture site, you will see that in the JUnit class, you can look at test singly linked list 02. I'm tracing this one together with you. This one's very interesting because somehow we're going to add first. So the order of the node we're going to build will be, rather than Tom, Mark, and Alan, it's going to be Alan, Mark, and Tom because we'll keep adding first. And that's why I want to trace this one also together with you to give you more insight. All right? Let's now take a look. Let's now try to visualize what's going on here. Let's start with the simple one, right? The first 3 lines over here is just to make sure we got an empty singly linked list. And if you guys remember just before the break, we spoke about what does it really mean when a singly linked list is empty, right? So now we just don't have just the head. We also got tail, we got size. Everything is default value. That's an empty singly linked list, right? Let's now visualize it. And we'll go from there. So what we have is we have a list over here. So the list is pointing to some singly linked list. By the way, I also put this important question here that you should always keep asking yourself. Is this method here going to also change the tail and size? Obviously it will, but we're going to see exactly how. Right? It's a question you're going to keep asking yourself. Are the attributes kept consistent with each other? So this one here is going to be singly linked list. And then I'm just going to put a head and tail right here. Okay, you know what? I'll give myself a little bit more space. And I'll put it here. All right, Just remember that's a question we got to answer at some point. All right, I put it there. And I got the syncly linked list, and then I got head, tail, and size. 3 attributes. Let's put the size over here, and then the head over here, and the tail over here. Now, how do we represent an empty list? Size should be 0, head should be pointing to null. Also, the tail should be pointing to null. Right? Like that. That's an empty list, which is important to visualize. And then, before we try to trace the 3 consecutive call at first, right here, let's try to understand roughly what's going on here. So this one here, you want to make sure you understand approach number 1, right? We're creating a new node, and then we're passing the next reference over here, not now, the current head, right here. Well, we're going to see exactly how that works. And then we have some special case over here to say if we are trying to add first into a list where currently it is empty. What does that mean? That means the new node is going to be the head and tail at the same time after the insertion. And then update the size. That's it. Right? Not difficult. All right, let's trace that completely. Line number 1. Let's say we want to add first Tom. Right here. How do we do that? So add first Tom. When we say head is assigned to new node. So you got to execute this part here first, right? The new node. So let's create a new node, which will be Tom. So Tom, I know that he's going to be at the end, so I'm going to draw him here. So this one here is going to be node. And then I got elements and next. Elements and next. And be careful. The element here is going to be Tom. That one's easy. So element here would just be Tom. Right? That's all good. And then the next for this node here is going to be the current head. What's the current head? Null. Right? And then I'm saying that once I got this expression done, the new head is going to be this new node. All right? So think about this part over here is really this part here to set it to be null. And then this part over here is going to set the head right here. This will be number 2, which is the variable assignment. Well, that one's important. Hopefully everybody getting it, right? That's good. And also you can see that currently the size is equal to 0. That's a special case. So after this insertion here, the list has only one node. So that node should be head and tail at the same time. So tail will be equal to head. Number 3. Tail will be equal to the head. Number 3. And number 4, update the size from 0 to 1. That will be number 4. So you can see this method call for the at first for the first time involves 4 steps. There will be one extra step over here because size currently is 0. Normally the size is already not empty. You don't really need that extra like a special case. All right, things are going to get a little bit messy, I'm afraid. But hopefully you're following, right? We got 2 more to execute. At first, mark. All right, so what we do is we're going to execute at first. So we're going to execute this line here. We're still going to create this new node over here. And the nodes next will be the head currently, which is the Tom node over here. So I'm just going to put the node right here. Okay. Okay. You know what? How about I put it here, right here. So this node over here is going to be going to have element and next, element and next. So this will be mark. And what about the next? Next is going to be the current head, right? Current head. The current head is this node over here. So that means that node's next will be just right here. So think about that one there is the 1 for the blue, right? The 1 for the blue. And is the current size equal to 0? Not really. So don't worry about special case. Skip. And then we can increment. Oh, sorry. I forgot one. Shame on me. So over here. You can see this one here. Remember, right? We just created this node here. But I got to make sure I update the head. Right? Head is going to be assigned to this particular new node. So we're going to say head, rather than pointing to over here, is now going to point to right here. So that's the second step for the blue. Second step for the blue. And then we skip this part here because size is not equal to 0. And then we're going to increment the size from 1 to 2. So that's step number 3 for the blue. Let's see what's happening right now. After this, you can see the head is pointing to this node. That node's next is pointing to this node, whereas the tail remains to be that node. So the list makes sense. Finally, let's take just 1 minute, if I may. Finish that. Okay, Alan, let's finish that very quickly. So for this Alan here, we're just going to create, okay, let me put it here, right? Alan. Okay, we're going to get node here. So we got elements and next. Elements and next. So element will just be Alan. And when you execute this expression over here, that's going to be the 1 for pink. Next reference will be the current head. The current head is right here. So it's going to be pointing to right here. And then step number 2 for the pink will be we're going to change the head, right? So the head right now, rather than pointing to the blue, is now going to point to the pink right here. All right, so that's the number 2 for pink. And size is actually equal to 2, not 0. So we also skip. And then we're going to execute this one here. That'll be step number 3. Change from 2 to 3. All right, so that's step number 3 for the pink. So what have we got? We have got the following, quickly. So the head is pointing to right here. And the tail is pointing to right here. And then the head is pointing to the next, and the second node is pointing to the third. That's the final pointers we have. I would suggest try to trace better than I have to draw a nicer diagram to really convince yourself what's happening here. All right, if you check all the assertions afterwards, they all make sense. All right, thank you. I will see you on Tuesday. And start with the assignment number 2.